Hello, and welcome to Chemistry with Swag. Our topic today will be acids and bases.
Professor Flash, what are acids and bases?
Great question, Govin. An acid, by the Arrhenius definition, is a solution with a pH of less than 7 that produces H+ ions in solution, whereas a base is a solution with a pH greater than 7 that produces OH- ions in solution. So, there are strong acids and strong bases. Strong acids and bases dissociate completely, whereas weak acids and bases only ionize partially. As you can see, we have a list of the strong acids and strong bases on the board.
Oh, you're so buff! You know what else is buff, guys?
Buffered
solutions!
Can you please tell me what a buffer is?
Buffered solutions resist changes in pH when H+ or OH- ions are added. The components of a buffer solution are either a weak acid and its salt or a weak base and its salt.
Well done.
Thank you.
Now let me explain a little bit further. Say we have a solution. We put a salt in there. We're going to use NaC2H3O2. That's going to dissociate into Na+ ions and C2H3O2 ions, O2- ions. We're also going to have some leftover HC2H3O2 in there as our weak acid. Therefore, when we add H+ ions, such as in HCl, the H+ ions will bond with the C2H3O2- to produce this. That resists the change in pH. Also, if we were to add, now say we add NaOH, a strong base. This will produce OH- ions in solution. That, in a normal solution, would cause a change in pH. However, in a buffer solution, it would simply remove the H+ ion from the C2H3O2- and produce H2O. That resists a change in pH. Does anybody know how to prepare a buffered solution with a certain pH?
Me!
Shaniqua, come on down. Very good, Shaniqua. Now can you please explain how you did that?
Okay, so we're calculating the ratio of the acid to its salt required to yield a pH of 4.30 with benzoic acid. So to do that, we first found the concentration of H3O+, which is 5.0 times 10 to the negative fifth. We then plugged that into the equilibrium expression, which is products over reactants. And once we did that, we found the ratio to be 0.78. Yay.
And now, an excerpt from Professor Shorty McShortshorts, who was out sick today.
Professor Shorty McShortshorts here today, and I'm going to talk to you about my homies Henderson and Hasselbalch, and how they derived their awesome equation calculating the pH of a buffer solution. First, they started with a weak acid, HX, and one of its salts, which we'll call MX. They placed the weak acid in water and yielded hydronium ions as well as the conjugate base X-. Then they wrote the Ka expression, which equals the concentration of the products, hydronium ions, and the conjugate base over the concentration of the reactant, so HX. Then they manipulated the formula in order to solve for hydronium ions, the concentration of hydronium ions. That equals Ka times the concentration of the weak acid divided by the concentration of the conjugate base. Now, here's where they did something a little bit crazy. They took the negative log of both sides. Therefore, they had negative log of the concentration of hydronium ions equals the negative log of Ka minus the log of the concentration of weak acid divided by the concentration of conjugate base. Now, they looked at it and said, that looks pretty ugly. And then they were like, wait a minute, isn't the negative log of hydronium ions just pH? And isn't the negative log of Ka just pKa? Of course it is. So, they were able to erase all this ugly stuff. Here we go. We are erasing it now. And they could rewrite the expression as pH equals pKa minus the log of the concentration of weak acid divided by the concentration of the conjugate base. Now they looked at this and said, it's still a little ugly. I want to get rid of this negative sign and switch the numerator and the denominator. So, once again, they went back to the drawing board and were able to come up with their final equation of pH equals pKa plus the log of the concentration of conjugate base divided by the concentration of the weak acid. Here is your Henderson-Hasselbalch equation to calculate the pH of a buffer solution. Thank you for joining me today.
Now my boy G Money is going to explain us some titration curves.
Yeah. Alright, so a titration curve shows the relationship between the pH of a strong acid and strong base. It shows how the pH raises as you add more titrant. In this case, it's a base. At the equivalence point is when the strong acid and strong base, they have equal number of moles. With a weak acid and strong base, however, the pH is above 7 because there's more, since there's equal number of moles of strong base and weak acid, the pH raises. Now we'll, wait.
And now, a guest speaker bringing us a titration demo.
A titration is a controlled acid-base neutralization reaction. 20 milliliters of hydrochloric acid of an unknown molarity is added to a flask. 2 drops of indicator dye are added to the acidic solution. This indicator dye is clear in acidic solution and pink in basic solution. The burette is filled with a sodium hydroxide solution of known strength and an initial reading is taken. The base is added to the acidic solution until the solution stays a slightly pink color. At this endpoint, a final reading is taken. The moles of base added equal the moles of acid present. This same reaction can be followed using a pH meter instead of an indicator dye. Initially, the pH changes very little as base is added. Suddenly, the pH changes rapidly as the endpoint passes. The solution quickly becomes very basic, and again the pH changes very little. The endpoint occurs at this middle point on the curve.
Slide Master Flash.
Hey.